Hi everyone, this is Mrs. GA, and today we're going to be solving exponential equations using logarithms. Alright, I have a quick warm-up for you guys, so please pause the video and give these a try on your own. It's a little review of our last lesson. Alright, go ahead and check your answers here. For part A, we can use that power property, and then we can evaluate this logarithm, which is equal to 2, so 4 times 2 is 8. For part B, we can use that quotient property. So remember, when there's two logarithms that are separated by a difference, so with subtraction, we can condense them into a single one using division. So notice here we have a single logarithm and division within the logarithm. And if you simplify this, it's 32. So then we can evaluate this logarithm. 2 to what power is 32? 5. Then here we can use that power property. So remember, when logarithms are separated with addition, we can condense them into a single logarithm that is a product of these three values. So log base 8 of 64, and then we can evaluate from there, giving us 2. If any of these properties or evaluating seems tricky to you, make sure you go back and rewatch some of those previous videos so you can relearn those skills. Alright, so today we're going to be solving exponential equations, and the way that we will do this is using logarithms. So here are the steps in which we're going to follow today. So first we're going to isolate the exponential term, so the term that has your variable, and it is going to be up in the exponent. So once you have isolated it, we're actually going to rewrite the equation in logarithmic form. So we have two options, and I'll show you both, or we can take the log of both sides. So when you take the log of both sides, you can pick whatever base you want for your logarithm as long as it's the same on both sides. So a little tip, it's really helpful to match the base of your logarithm with the base of your exponential expression, because it simplifies away really nicely. So after you've either rewritten or taken the log of both sides, we keep simplifying. We're going to use some of those properties that we just practiced, and then we should be good to go. One last thing, if I ever ask for an answer in decimal form, that means that it's something you can't evaluate by hand, so you will need to use your calculator. And for most scientific calculators, they can only do common logs or natural logs, so this change of base formula is going to be really important for us to be able to get that decimal approximation. So here's a little reminder of what our change of base formula is. Alright, so we're going to give 2 a try on our own. So here we're going to solve. We're going to give an exact answer, meaning no decimal, so it might have logarithm in it. And we're going to give a decimal answer rounded to the nearest hundred, so we'll use our calculator. So let's look at this first one. Remember, step 1 is to isolate our exponential term. So we're trying to isolate 2 to the power of 3x. And note, you cannot multiply the 5 and the 2 according to PEMDAS, order of operations. We always do exponents before we multiply, so you cannot multiply 5 times 2. We can, however, get rid of this 5 by dividing both sides of our equation by 5, leaving us with 2 equals 2 to the power of 3x. So for this problem, there's actually quite a few different ways we can finish solving. One thing you might notice is that we have the same base on both sides. So when that happens, if you have two expressions with the same base that are equal, that means that their exponents must also be equal, right? So this exponent, which is just a 1, must be equal to this exponent. So one way of solving this equation is kind of with logic and saying we can set the exponents equal to each other. So 1 equals 3x, and then we can divide by 3 on both sides. So that's one way of doing it. However, it only works because the bases are the same. So let's say the bases are not the same. One thing we can do is, remember, take the log of both sides. Now, since this has a base 2, I'm going to choose to take log base 2 of both sides. So log base 2 of 2 equals log base 2 of 2 to the power of 3x. So in this, on the left side, log base 2 of 2 is 1 if we evaluate it. And here, remember, if our bases match, base here and base here, it can simplify to whatever is in the exponent. So 3x, and you can see we get the same exact answer. X equals 1/3. So there is that one other method for solving these exponential equations. We can rewrite this as a logarithmic equation. So we see that the base is 2, our exponent is 3x. So remember, logarithms define exponents. So 3x equals log base 2 of 2. And then we can simplify and finish solving from here. Log base 2 of 2 is 1. And again, we get the same exact answer. So 3 different ways here. Again, just a quick recap. If the bases are the same and the terms are equal, then the exponents must be equal. That's kind of our common sense method. This method was taking the log of both sides, and this time I chose log base 2 to match our base. And then the third method is actually rewriting this exponential equation as a logarithmic equation and simplifying. So it just depends on what works best for you for the given problem. All right, let's try another one together. So here we have 15 equals e to the power of 2x plus 1 minus 5. So remember, our first step is always to isolate our exponential term. So we can do that pretty easily by adding 5 to both sides. So 20 equals e to the power of 2x plus 1. So again, we have 2 different methods here that we can use. This one, the bases aren't the same, so we can't do that common sense method. So let's start by taking the log of both sides. We'll do it both ways again so you can decide what you like best. Now, since this is a base e term, when I take the log of both sides, I'm going to choose base e, which is natural log. So we take the natural log of both sides. Natural log of 20 equals the natural log of e to the power of 2x plus 1. Just remember, natural log has base e. So on the left side of our equation, this will stay natural log of 20. And then on the right side, remember, if the bases match, your answer is whatever is left over, so 2x plus 1. And then from here, we just need to finish solving for x. So subtract 1 from both sides. So we have natural log of 20 minus 1, so this minus 1 is outside of the natural log, equals 2x. And last, we're going to divide both sides of our equation by 2. So x equals natural log of 20 minus 1 all over 2. So this actually would be our exact answer. And this is as much as we can do by hand because we can't evaluate by hand the natural log of 20. However, we can plug this into our calculator to give us a decimal approximation. So let's do that really quick. And if you are rounding to the nearest hundredths, in the calculator it shows 0.997. So this actually would round to 1.00. And we do actually need to write out 1.00 to show that we did round it to the nearest hundredths. Now, if you don't really like this method, let's try that other method of rewriting as an exponential equation. So our first step will always be the same. Now from here, let's try rewriting it. So our base is e, our exponent is 2x, and the result is 20. So remember, logarithms define exponents, so that's what it's going to be equal to. Since the base is e, we do natural log, and the result is 20. So you can see that it leads us right to this step right here. And then we finish solving the same way. So whether you want to take the natural log of both sides, or whether you would prefer to rewrite it as an as a logarithmic equation, either way it's about the same amount of work and you end up with the same result. Alright, at this time I'm going to ask you to pause the video and give these two a try. Remember to give an exact and a decimal answer. And I do encourage you to try using both methods just to get that practice, and then you can decide later on which one works best for you. Alright, go ahead and check your work here. So remember, our first step is always to isolate, and then from there you have two options. So here I took the natural log of both sides. I picked natural log because here we have base e. And then from there we can simplify and finish solving. So here's the exact answer. and here's the decimal approximation. If your decimal approximation doesn't match mine, check to make sure that you've grouped everything properly in your calculator. Alternatively, from here, you could rewrite it as a logarithmic equation. So the exponent is x minus 1, it's base e of 1/2. So you end up with the same exact step here. For part B, again, isolate. So we multiply both sides by 10. And then here I took the common log of both sides. Common log because this is base 10. So I always recommend that your logarithm's base match this base. So common log of both sides. And then we can simplify this and finish solving. Or take this exponential equation and rewrite it as a logarithmic equation, which you get the same exact thing. So this is our exact answer, the log of 20 divided by 4, and here is our decimal approximation. Again, make sure you're doing the log of 20 and then closing the parentheses before you divide that by 4. All right, let's try a couple more together. So again, we're going to solve and we're going to give both an exact answer and a decimal answer. So this first one we have 4 equals 24 to the power of x over 5. So again, we have two different ways we can approach this. Let's start by taking the log of both sides. So again, since this is base 24, I'm going to recommend to take the log of base 24 both sides. Of course, you can do whichever log you want, but this is the most convenient way, I think, to simplify. Okay, so now we can simplify this portion of our expression. Remember, if the bases are the same, it simplifies to the exponent. So it's x over 5 equals log base 24 of 4. And then we multiply both sides by 5. So x equals 5 times log base 24 of 4. So from here, there's no way for us to simplify this by hand. So this is what we would call an exact answer. And then we can get a decimal approximation by plugging this into our calculator. However, again, most calculators can't do log base 24. They can only do common log or natural log. So we're going to rewrite this using our change of base formula. So it'll be x equals 5. So remember, for change of base formula, the base number goes to the bottom. So it's log of 4 divided by log of 24. And this is what we'll plug into our calculator to get our decimal approximation. So we should get approximately 2.18 if we round to the nearest hundredths. Now, of course, we can do this a different way. Instead of taking the log of both sides, we can directly rewrite this as an exponential equation. So the exponent, x over 5, equals log base 24 of 4. And you'll see that we have the same exact thing. So either way, you end up with the same answer. Okay, let's look at this next one. So again, we're going to look at the two different ways we can approach this. Let's start by taking the log of both sides. So for our exponential expression, it is base 7. So I recommend taking the log base 7 of both sides. So log base 7 of 10 equals log base 7 of 7 to the power of 4 times x plus 5 divided by 3. So again, this simplifies to simply whatever's in the exponent. So we have log base 7 of 10 equals 4 times x plus 5 over 3. And now we just need to finish solving for x. So we can multiply by 3 and divide by 4 in the same step. We're multiplying by the reciprocal. So 3 over 4 times the log base 7 of 10 equals x plus 5. And then our last step would be to subtract 5 from each side. So 3/4 log base 7 of 10 minus 5. And I put the parentheses around here to remind you when we plug this into our calculator to make sure to close off your logarithm before you subtract 5. This minus 5 is not part of the inside of the logarithm. So again, this would be our exact answer because we can't evaluate this any further by hand. So from here, we do need to plug this into our calculator. This, again, most calculators cannot do log base 7, so let's rewrite this using the change of base formula. So the 3 is in the numerator here, and then log of 10 will be in the numerator. And common log of 10 is 1, so that simplifies nicely. 4 is in the denominator, and then the log of 7. So log base 7 of 10 can be written as log of 10 divided by log of 7. That's our change of base formula. And then from that entire thing, we subtract 5. So go ahead and plug this into your calculator. Okay, and if we round it to the nearest hundredths, we should get approximately negative 4.11. Again, when you're plugging this into your calculator, make sure you're grouping things appropriately, especially the denominator. You do need to have parentheses around this entire thing. If you forget these parentheses, your calculator will only divide by the 4, and then it will multiply log of 7 because it is following order of operations. So be really careful here. If you're not getting this answer, means you're plugging it in wrong. So keep trying until you're able to get it. Alternatively, again, instead of taking the log base 7 of both sides, we can directly just rewrite this as an exponential equation. So again, our exponent goes here, 4 times x plus 5 divided by 3, because logarithms define exponents, equals log, the base is 7 of 10. And you can see that we end up with this. And then we would finish solving in the same exact way. So here's 2 examples where you can see we do need to use that change of base formula here and here to help us get a decimal answer in our calculator. All right, here's our last example. We're going to try a real-life example that will require us to solve an exponential equation. So it says, suppose that $250 is deposited into an account that pays 4.5% compounded quarterly. So here's the equation. A equals P times 1 plus R over N to the NT. So A is the amount in the account after T number of years with an initial investment of P, that's our principal, that earns an interest rate of R, so this would be R as a decimal, not a percent, and then N is the number of times that it's compounded. So in this case, since it says it's compounded quarterly, we would say that N equals 4. So they're asking us to solve for T to find how long it will take for the account to contain at least $500. So we're solving for T, and then A will be 500 because that was the amount that we're trying to reach. Our principal, our initial amount is 250, and our interest rate, 4.5% written as a decimal, is 0.045. So let's substitute those values. So we get 500 equals 250 times 1 plus 0.045 divided by 4 to the power of 4t. And we're solving for t. We're seeing how long does it take for our money to grow from 250 to 500, or essentially to double. So you can see this is an exponential equation because our variable is in the exponent. So let's start by, let's try to isolate this. So we're going to divide both sides by 250. So that gives us 2 equals, now we can simplify what's inside these parentheses, so it becomes 1.01125 to the power of 4t. So you can see here is our exponential equation. So let's, instead of taking the log of both sides, since our base is kind of strange, let's rewrite this as an exponential or a logarithmic equation. So our exponent is 4t, so logarithms define exponents. So the log of base 1.01125 of 2. And then our last step will be to divide both sides by 4. So we're dividing that entire logarithm by 4. All over 4. Now for us to be able to plug this into our calculator, because of course we don't want an exact answer for this, we need a decimal because it's a real life problem. No one would be able to interpret what this means. We are going to rewrite this portion using the change of base formula. So we'll do log of 2 over log of 1.01125. So that will go in the denominator with the 4. So t equals the log of 2 divided by the 4 times the log of 1.01125. And again, we're using common log when we do the change of base formula because most scientific calculators can compute common logs. All right, let's plug this in, being really, really careful to group our denominator so our calculator can follow order of operations. And we should get approximately, I'll round to the nearest tenths for this one, 15.5. So we'll take about 15 and a half years for our money to double. All right, so that is all for today's video. Thank you guys for watching.